I will share my slides now. Is my slides visible?
Yes, ma'am.
Okay. So, welcome to NPTEL PMRF tutorials, week 2 assignment solving session of Introductory Organic Chemistry to August 2023. The instructors for this course are Professor Harita Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. So last week we have discussed regarding essentials of NMR spectroscopy and some of the problems of electrophilic aromatic substitution reaction. We have solved previous year assignments of week 1, and if anyone having any doubt regarding last week, you can come up with that. Any doubts? If no one is having any doubts, we can go to week 2 assignment solving session. So first of all, we will be discussing the summary of lectures that are discussed in week 2, followed by we will be solving previous year assignment questions of week 2. Is it okay?
Yes, ma'am.
Okay. So coming to the summary of week 2, in week 2 we have discussed electrophilic aromatic substitution reaction in phenol and electrophilic aromatic substitution, effect of electron donating groups and effect of electron withdrawing groups, followed by nucleophilic aromatic substitution reaction, which was discussed in two lectures. Then a special topic was discussed, that is Hammond's postulate and essentials of IR spectroscopy. So, I will be discussing briefly what was discussed in week 2. So, in electrophilic aromatic substitution in phenol, compared to benzene, phenol is a activated system because of this lone pair of electrons that can involve in conjugation with the pi electron cloud of benzene. So, this lone pair of oxygen can delocalize in this fashion. So, there will be a negative charge generated at the center. Then, when it is delocalizing in this fashion, a negative charge will be delocalized at the center of this aromatic ring. When it will delocalize, it will generate a negative charge at the center. So when we conclude, there will be a net negative charge at the ortho positions, which are adjacent to this OH group, and at the para position. So if we are carrying out electrophilic aromatic substitution in phenol, for example, if we are carrying out a bromination reaction on phenol, so this is phenol, and if we carry out bromination reaction in presence of bromine and ethanol, the system is highly activated, and hence it will undergo bromination at the three positions, that is the two ortho positions and the para position. So I think you might have seen the mechanism for this in week 2 lectures. Mechanism will be similar only. So
Yes, ma'am.
when this lone pair of electrons will be delocalizing, this double bond will break and it can go and attack the bromine, or like it can delocalize and first it can attack from the para position. Anything can happen. So it will be uh, brominating at three positions in case of phenol. But in case of benzene, bromination under normal conditions are not possible. We need a Lewis acid for the reaction to take place. Now coming to electrophilic aromatic substitution, effect of electron donating and electron withdrawing groups. So this is the summary of what was discussed in the lectures. So if we are having electron donating groups like Nr2, OR, etc., which can undergo uh, donation of electrons by conjugation, they are very activating in nature towards electrophilic aromatic substitution reaction, and they direct the electrophilic aromatic substitution at ortho and para positions only. And in case of alkyl groups, which can undergo donation by inductive effect, alkyl groups like methyl, secondary alkyl or tertiary alkyl, they can undergo donation by inductive effect. So they are activating in nature when we consider electrophilic aromatic substitution reaction. They can undergo mostly ortho and para substitution, but in some cases meta substitution will also take place. In case of halogens like fluorine, chlorine, bromine, and iodine, they can undergo donation by conjugation and withdrawal by inductive effect. So it can undergo conjugation because of the lone pairs that are present on these halogens. Fluorine, chlorine, bromine, iodine, etc. will be having lone pair of electrons present on them, right? So they can undergo donation by conjugation and withdrawal by inductive effect. Inductive because of the electronegative nature of these atoms, they can undergo withdrawal by inductive effect. So the atoms, so this functional groups like fluorine, chlorine, bromine, and iodine, they are deactivating in nature if we consider electrophilic aromatic substitution. So they undergo ortho and para substitution, mostly para. And if we consider CF3, NR3 plus etc. Groups like CF3, NR3 plus etc., they will undergo withdrawal by inductive effect. They are electron withdrawing in nature by inductive effect. So they are deactivating in nature if we consider electrophilic aromatic substitution, and they will undergo meta substitution only. And if we consider functional groups like nitro, nitrile, COR, SO3R, etc., they will undergo withdrawal by conjugation because they are having a conjugation possible. So they will undergo electron withdrawal by conjugation. So these groups are very deactivating in nature if we consider electrophilic aromatic substitution, and they will undergo meta substitution only. So this was what was discussed in two lectures regarding electrophilic aromatic substitution, effect of electron donating and electron withdrawing groups. Is this clear for everyone?
Yes, ma'am.
Okay. So next what was discussed was nucleophilic aromatic substitution reaction. So there were two mechanisms that were discussed. If electron withdrawing groups like nitro groups, cyanide groups, etc. are present, it will undergo addition elimination reaction mechanism. So here a nitro group is present. So this alcohol OH minus will add at this ipso position of the chlorine. Ipso position means that is the same carbon as that of the chlorine. Then it will add on to ipso position of this chlorine. This double bond will break and it will delocalize into this position. Then this double bond will break and it will delocalize into this position. Then N double bond will break and it will give negative charge on this oxygen. So now an intermediate have formed. So now this aromaticity of the system is disturbed. So we have to regain the aromaticity. For that, this lone pair of oxygen will fall down. This double bond will delocalize into this position. This double bond will delocalize into this position, and the leaving group, that is the chlorine, will leaves. So we will get this compound as the product. So here we can say that an addition elimination reaction mechanism is taking place, or an addition substitution mechanism is taking place, because addition is taking place and substitution, that is the chlorine is substituted by the alcohol. Okay. And the benzene mechanism, uh, so if electron withdrawing groups are absent in the system, so the benzene mechanism is likely to take place. So here, uh, and thus take place under harsh conditions like sodomite condition, ammonia, in liquid ammonia condition, etc. So this in NH2 minus, it can abstract the proton that is adjacent to this bromine. So it will generate an anion at this position with full sp2 orbital. So this anion can delocalize in this fashion and eliminate this leaving group, that is bromide. So this intermediate benzene is formed. Benzene is highly reactive. So this intermediate, it can undergo nucleophilic addition of this amine group. So after addition of this amine group, a negative charge will be formed at this position. This negative charge can abstract protons from ammonia that will be present in the system, and it will lead to formation of this aniline. So the bromobenzene was converted into aniline in this reaction. Clear?
Clear, ma'am?
Okay, so this was discussed. This was what was discussed about nucleophilic aromatic substitution reaction in week two. Then Hammond's postulate was discussed. So, discussing about the Hammond's postulate, it gives information about structure of the transition states. Hammond postulate gives information about the structure of transition state. It says that two states that interconvert directly are directly linked in a reaction profile diagram, and that are close in energy are also similar in structure. If we consider a reaction profile, like this is the starting material, this is the product, and this is the intermediate. So here the intermediate will be resembling the product because the product is closer in energy to that of the intermediate, so the structure of the intermediate will be similar to that of the product. So this is what Hammond postulate is stating. So a transition state will be most like the starting material, the intermediate or the product, if it is close in energy to one of these observable structures. So here, if we are considering this transition state, so this will be close in energy to that of the intermediate. So this transition state structure will be similar to that of the intermediate, and this transition state, it is closer in energy to that of the intermediate, so its structure will also be similar to that of the intermediate. Intermediate is closer in energy to that of the product, so its structure will be similar to that of the product. So when we are considering a highly exothermic reaction, highly exothermic reaction means the product's energy will be lower than that of the starting material. So the transition state will resemble the starting material. So the product's energy will be much lower. So the transition state will resemble the starting material in case of highly exothermic reaction. So whatever we have represented here is a endothermic reaction. So in case of highly endothermic reaction, transition state will resemble the product. So this is what the Hammond postulate is all about. I think Hammond postulate is clear for everyone. Then finally, essentials of IR spectroscopy was discussed in the last lecture. So the main equation that was used here is mu equal to 1 by 2 pi c root of f by nu, where nu equal to the reduced mass, which is denoted by m1 m2 divided by m1 plus m2. So here this nu is the frequency, f is the force constant, and this mu is the reduced mass. So here this equation is used in the case of um, spring system, etc., which is applicable in case of atoms that are connected with a bond. So if we consider two atoms that are connected by a bond, so if it is single bond, this f will be lower. So when we are discussing, this mu is proportional to root of f by mu. So if f increases, mu will increase, and if mu, that is the reduced mass, decreases, mu will increase. Is this clear?
Yes, ma'am.
So if we are having a single bond, so the force constant will be less compared to that of a double bond, compared to that of a triple bond. In case of triple bond, the force constant will be more, which will be lesser in case of double bond, which will be even lesser in case of a single bond. So the force constant is increasing if we are having a triple bond. So the frequency will also increase in case of a triple bond. And if we are having two different atoms, if we consider carbon carbon and carbon hydrogen, so here in case of carbon carbon, if we calculate mu equal to m1 m2 divided by m1 plus m2. For carbon, uh, mass is 12, so 12 into 12 divided by 12 plus 12, which is equal to 6 in case of this carbon carbon single bond. If we consider carbon hydrogen, this will be 12 into 1 divided by 12 plus 1, which is equal to 12 by 13, that is less than 1. So in this case the mu is lower, so the frequency will be higher in case of carbon hydrogen single bond compared to that of carbon carbon single bond. Is this clear? So what we have to keep in mind is, if the force constant is increasing, the frequency will be increasing, and if the reduced mass mu is decreasing, then the frequency will be increasing. So let us see a chart where we will see the C single bond C, C single bond O, and C single bond N are present in the region between 600 to 1400 centimeter inverse. Wave number equal to 1 by nu. Okay. So these C single bond C, C single bond O, C single bond N, etc. will be present in between 1400 and 600 centimeter inverse. If double bond is coming, C double bond C, C double bond O, C double bond N, etc. is coming, the frequency will be increasing. Frequency will be increasing as we have seen in the equation. So this is present in between 1600 and 1800 centimeter inverse. This number is the inverse of wavelength, 1 by lambda. Then if triple bond is present, like C triple bond C, C triple bond N, etc., it is present in between like 2000 and 2500, like a small region in between that. And if one atom is smaller, like as we have seen in case of mu of ch and cc. If one atom is smaller, then it will be present in the region between 2500 and 3500, as we can see here, NH, OH, CH, etc. This is the basic concept of IR spectroscopy. What we have to keep in mind is that equation mu equal to 1 by 2 pi c root of f by nu, where f is the Fogg's constant and mu is the reduced mass. So for references for this week 2 lectures, you can follow Claydon Organic Chemistry, Chapter 22 for Electrophilic Aromatic Substitution, Chapter 23 for Nucleophilic Aromatic Substitution, and Chapter 3 for Essentials of IR Spectroscopy. So the summary is clear for everyone?
Yes, ma'am.
Okay. Now coming towards the assignment problems. This is question number 1. The order of reactivity in the following series of compounds, where X denotes substituents indicated in the options below. X can be anything of this, like NO2, CN, COMe, and Me, towards nucleophilic aromatic substitution. So we have to see the order of reactivity when X is NO2, X is CN, X is COMe, X is Me. So what will be the order of reactivity for this nucleophilic aromatic substitution reaction? So this X can be anything like NO2, CN, COMe, or Me. So what will be the mechanism for this nucleophilic aromatic substitution reaction, and what will be the factors that will be influencing the stability or the rate of the reaction? So more stable the intermediate, lesser will be the energy barrier towards its formation. If the intermediate will be stabler, so the intermediate, if we will see, we will be seeing the mechanism of the reaction. In that case, if the intermediate will be stable, the energy barrier will be less, as we have seen. So we have seen, like, if this intermediate is stabler, then this energy barrier will be less towards the formation of of this intermediate. So the more electron withdrawing ability, it better stabilizes the negative charge on the intermediate. So we can see the mechanism. So we are having pyrrolidine. The lone pair on this nitrogen of pyrrolidine can attack at this ipso position of the fluorine. Then this double bond will break and it will migrate. So here there can be a negative charge, like here there can be a negative charge, here there can be a negative charge, as we can see. So uh, this double bond will be attacking here. Sorry, this lone pair of electrons on the nitrogen can attack at the ipso position of this fluorine. This double bond will migrate, so this double bond will come into conjugation with this X. Then when this will go back in this fashion, this F will be acting as the leaving group and it will be eliminated. So we will get the desired product, that is this one. So here uh, what should be the X, so that the intermediate will be more stabler? So in case of NO2, CN, COMe, and Me, which will be giving more stable intermediate by stabilizing the negative charge, which will be having higher electronegative, like higher electro withdrawing ability. Out of this four, that is NO2, CN, COMe, and Me, which will be highly electron withdrawing in nature.
Nitro.
Nitro will be highly electro withdrawing in nature, so this will come in first position. So this will be more reactive. The order of reactivity will be more in case of nitro for nucleophilic aromatic substitution reaction. Then with respect to cn come and me, which will be more electron withdrawing?
Cyano.
Cyano will be the next electron withdrawing. Then comes COMe, and Me is not electron withdrawing. It is electron releasing with respect to inductive effect. So this will be the least. So when we are considering the order of reactivity, the if X is coming nitro, the order of reactivity will be more NO2. Then if X is cyano, it comes the next. If X is COMe, it will be the next. And if Me, it will be the least. So the order will be NO2 greater than Cn, greater than COMe, greater than Me. Is this clear? So the correct answer will be NO2 greater than Cn, greater than COMe, greater than Me. Any doubt?
No, ma'am.
Okay. Now coming towards the second question, which of the following mechanisms of action occur when there are electron withdrawing groups on the aromatic ring during nucleophilic substitution? So we have discussed when we were discussing the summary of the lectures, when electron withdrawing groups are present in the aromatic ring during nucleophilic substitution, which mechanism is likely to occur? Addition elimination, elimination addition, substitution addition, addition substitution.
Addition substitution.
Addition substitution will be the right answer. We have seen it as addition elimination, but as we can see in the mechanism, the hydroxyl group will be replacing the chlorine. So it is substituting the chlorine. That is why we will say it is addition substitution reaction. So first the hydroxyl group will add at the ipso position of the chlorine. Then this double bonds will be migrating in this fashion. They will undergo conjugation with the nitro group, and when the oxygen lone pairs will be coming back, this leaving group chloro will be eliminated, or it will be substituted by this hydroxyl. So the mechanism will be addition substitution. This is clear. Any doubts?
Nothing, ma'am.
Okay. So now coming to the third question, determine the product in the given nucleophilic aromatic substitution reaction. We have 2 2,4 dinitrochlorobenzene, and it is treated with ethylamine and heated. So what will be the product? Four options are given. So what will be the likely product? If we are considering this as option A, option B, option C, and option D, what will be the product?
Option A.
Option A. So here, what you have to understand first is, in case of EtNH2, Et will be Et plus and NH2 minus. So NH2 minus will be the nucleophile. Nucleophile will be negatively charged species, or species that are having lone pair of electrons on them. So this Et plus cannot incorporate into the system. Either NH2 minus will be adding onto this chlorine and eliminating, or what will be the mechanism, we will see. So option A we cannot
Option
the
B.
correct answer. So option B will be the correct answer. We will see the mechanism for that. So first, NH2 minus will add at the ipso position of this chlorine. This double bond will migrate in this fashion. So here a negative charge will be generated. That negative charge will delocalize in this fashion and this double bond will migrate. So here a negative charge will be generated. So then this negative charge will undergo conjugation with this nitro group and this N double bond will break and this negative charge on the oxygen will be generated. So this is the intermediate that is formed. Now here the aromaticity of the system is lost. So we have to gain the aromaticity of the system back. So this lone pair of electrons on the oxygen will fall down. This end double bond C will break and this double bond will migrate into this position. This double bond will migrate here and this CCl bond will break and Cl minus will be leaving. So we will get this substituted product like NH2 will be substituting Cl minus. NH2 minus will be substituting Cl minus and addition substitution reaction or addition elimination reaction is taking place here. So the correct option will be option B, where NH2 minus of this EtNH2, where NH2 minus is the nucleophile, will be replacing this Cl. Is this clear?
Clear, ma'am?
Okay. So the next question is the major product of the following reaction is. Here they have given a substituted benzene ring and this acetic anhydride in presence of AlCl3. What will be the major product that will be forming? A, B, C or D? So someone have texted that C will be the right product. Yeah, C can be the right product. We will see the mechanism. Like, what is the name reaction that is taking place here?
Friedel-Crafts.
Yes, Friedel-Crafts acylation reaction is taking place here. So we will see the mechanism of the reaction. So first, this lone pair of oxygen on the oxygen will coordinate with this AlCl3. Then the lone pair on the adjacent carbonyl group will migrate in this fashion and this group will be eliminated. So acylium ion will be the key intermediate for Friedel-Crafts acylation reaction to take place. So we are having the acylium ion. So here this OCH3 will be the directing group. So the OCH3, this lone pair of oxygen, it will undergo resonance effect. This lone pair will undergo resonance effect. So this lone pair of oxygen will migrate in this fashion and at the fourth position, that is para position, it will go and attack on this carbon atom and this positive charge on the oxygen will be neutralized. So here this is the intermediate that is formed. So here the aromaticity of the benzene ring is lost. So here there is a proton base that will be present in the system will be abstracting this proton and the aromaticity is regained by neutralizing the positive charge on this oxygen. So we will get this product where acyl group is coming at para position with respect to this OCH3. Clear?
Yes, ma'am.
Okay. So this option C will be the correct answer in case of question 4. Now coming towards question number 5. The structure that contributes the most towards the stability of cationic intermediate during bromination is. They have given 4 different structures and which of these structure will contribute the most towards the stability of the cationic intermediate during bromination.
Option B.
Option B. Option B or D?
Option B.
B. So let us see the mechanism. So here, since NME2 it is an electron donating group, it will involve in conjugation with the system for undergoing this bromination reaction. So the lone pair of on the nitrogen will undergo delocalization. So it will push in this direction. So this double bond will break and a negative charge will be generated at this position. Then this negative charge will fall, as we can see by this arrow pushing mechanism, and a negative charge will be generated at the para position. Then this negative charge will fall, and a um, and this double bond will be breaking and a negative charge will be forming at this position. So overall there will be a negative charge at the ortho and para position and a positive charge on the NME2. Okay, so bromination can either take place at the para position or the ortho position, and a positive charge will be present on the NME2. So if we are considering like simply the like alkene double bond is going and attacking, so it will be as follows. It can go and attack, so a positive charge will be generating at this position. Then this double bond can migrate here, neutralizing the positive charge, so a positive charge will be generating here. Then this double bond can migrate and a positive charge will be generating here, but in this case the lone pair on the nitrogen is not involved. So in the case where there is a possibility for electron to come in conjugation with the aromatic system, it will undergo that conjugation. So here the positive charge will be present on the nitrogen like NME2 plus. So the correct option out of these four will be option D, where this lone pair of electrons on this NME2 will be involving, and the double bond will be going and attacking at the para position. Is it clear? Otherwise it is simply like the double bond will go and attack, so it is not having any sort of driving force for that reaction to take place. Here this lone pair of electrons on the nitrogen will be coming into conjugation with the system, thus increasing the electron density on the system, as we can see here. Okay, so the correct answer will be option D. Is it clear?
Yes, ma'am.
Okay. Now coming to question number 6, identify the reagents for the following reaction. So here the benzene ring is undergoing acylation. So it is you have to find out the reagents at this position A. Then it is undergoing chlorination at the meta position. So you have to find the reagents at position B. And then this double bond O, the ketone is reducing into alkane. So you have to find the reagents at C. Okay, someone have told like A equal to CH3COCl AlCl3. Yeah, Friedel-Crafts acylation reaction. Then B equal to Cl2 FeCl3. Yeah, it can undergo Friedel-Crafts alkylation sort of reaction. And C equal to Zn Hg bar HCl. A single amalgam can result in Clemmensen reduction, reducing this ketone into alkene. So this is the correct answer. So let us see the mechanism. So we have seen the mechanism for Friedel-Crafts acylation. So if there is an acid chloride in the presence of AlCl3, this chlorine will coordinate with this AlCl3. Then this lone pair of electrons on the oxygen will migrate in this fashion, and this AlCl4 minus is eliminated. So this acylium ion will be the key intermediate for Friedel-Crafts acylation reaction. So the double bond on this benzene ring can go and attack on this carbon of the acylium ion, and this bond will migrate so as to neutralize the positive charge on the oxygen. Then, in order to regain the aromaticity of the system, Cl minus, which will be present in the system, can abstract the proton that is adjacent to this acyl group, and it can neutralize this positive charge that will be generated on this benzene ring. So we will get acylation of this benzene. Then for electrophilic aromatic substitution, that is chlorination to take place. So we are having this electron withdrawing group. So we have seen that electron withdrawing groups can result in meta substitution, right? So this acyl group is meta directing group. So we will be getting chlorination at the meta position. This mechanism will be similar to that of Friedel-Crafts alkylation reaction. The CCl, this chlorine lone pair will coordinate with the FeCl3. Then this double bond can go and attack on the chlorine. Thus FeCl4 minus will be eliminating, and this will be neutralizing. Then it will undergo Clemmensen reduction, where in the presence of lead and mercury, that is the zinc amalgam in presence of aqueous HCl, this C double bond O will convert into CH2. So the mechanism of Clemmensen reduction we have discussed in last week. You can go into the YouTube video and see the mechanism of Clemmensen reduction. So as you have mentioned, the correct option will be CH3COCl AlCl3, that is Friedel-Crafts acylation reaction followed by chlorination using FeCl3 and Cl2. So here the COCH3, which is an electron withdrawing group, it is meta directing. That is why the chlorination is taking place at meta position. Then this zinc amalgam HCl condition, it will reduce COCH3 into CH2CH3. Clear for everyone? Any doubts?
No doubt.
Okay. Now coming into question number 7, the increasing order of reactivity of the following compounds towards electrophilic aromatic substitution is. So here we have four different compounds. This meta substituted CH3, para substituted CH3, then this fluoro compound and CHO. Option B you are telling. Option B will be the correct answer, because we have seen in that table that CHO will be electron withdrawing group. It is highly deactivating in nature. Then when we consider halogens, that is also deactivating in nature. Then these two CH3s are present. So when it is present at meta position, it will that effect of reactivity will be more compared to when they are present at the para position. So the correct option will be option B, where 4 less than 3 less than 2 less than 1. Any doubts? You can refer to the table that we have discussed in the starting, where we have discussed the summary. Anyone having doubts?
No, ma'am. Clear.
Okay. So now coming to question number 8, what is the major product of the following reaction? So we have this compound, it is undergoing nitration reaction in presence of concentrated HNO3 and concentrated H2SO4. So here they have given products with nitration at different position. So which will be the major product? I will mark
Option A.
A, B, C and D. Option A can be one of the product. but the correct answer will be option D, because it will undergo more resonance in case of nitration at this position when we consider. Let us see the mechanism here. As we have seen last week, the major key intermediate will be this nitronium ion. You can see last week's lectures for seeing how this ion is generated. So the lone pair of electrons on this bromine can delocalize in this fashion. So it will migrate in this fashion. A double bond will be formed here. This double bond will migrate into this position. This double bond will migrate into this position. This double bond will be migrate into this position. This double bond is going and attacking on this positively charged nitrogen, and this N double bond O will break, and a negative charge will be generated on the oxygen. So we have nitration that is taking place at this extreme para position. So now the aromaticity of this overall ring is lost. Two benzene rings is lost. So the base, sorry, this will be base. No H is there. So the base will go and abstract this proton. Then this bond will migrate here. This double bond will shift here. Then this double bond will shift here. This double bond will shift, and this double bond will be shifting here so as to neutralize the positive charge on the bromine, giving this product. So here, since the delocalization in this case is more, this nitration is taking place at this para position. This ortho product can also take place when this bromination, like when this is falling here, this can go and attack at this. So here also nitration can take place, but since delocalization is more in this case, so it will prefer forming this product as the major product. If they are asking what are the products that are possible, all orthopara products you can write, but this will be the major product where more delocalization is possible. So okay, you can ask the doubt. Shrejal, any doubts?
No, ma'am.
Okay. So since maximum delocalization is taking place in this case, that is why this nitro product will be the major product. So the correct answer will be option B, that is nitro at this extreme para position. Is this question clear for everyone? Any doubts?
Clear, ma'am.
Okay. Now going to question number 9. So here we have this 2-chloroanisole. So we are treating with sodamide in liquid ammonia. So what will be the product that is forming? So they have given four options. Option B will be the correct answer. So we can see what is the mechanism it is undergoing. So here this reaction is going through benzyne intermediate. So we have discussed the mechanism for benzyne formation when we were discussing the summary of the lectures. So we can go through what is happening. So the sodamide, here the nucleophile will be NH2 minus. So here NH2 minus can also act as the base, can abstract the proton. So the benzyne will be forming by leaving this chlorine. So this is the benzyne intermediate that will be forming. Now the NH2 minus, it can attack either from this position or from this position. Like OM is here, it can attack from ortho position or from para position. So When it is attacking from the ortho position, here the negative charge is forming here. So this negative charge is far away from this OMe, such that this negative charge can be neutralized by the electron withdrawing effect of this OMe. Since oxygen is a electronegative group, by inductive effect, this negative charge can be neutralized by OMe. So since this is far from OMe, this will not be possible. And also, since OMe is present, the attack of nitro from this position will be less feasible. Because of steric effect from this OMe, attack of NH2 minus, sorry, not nitro, NH2 minus from this ortho position will be less feasible. And also this negative charge that will be formed after adding of this NH2 minus, it cannot be neutralized by this OMe as it is far away from this OMe. So this product will be less feasible. Then when NH2 minus is attacking from the meta position, negative charge, this bond will be migrating here and a negative charge will be forming at this position. So by electron withdrawing nature of the oxygen atom by means of inductive effect, this negative charge can be neutralized by this OMe as it is adjacent to this OMe. Also, the steric effect is ruled out as NH2 is attacking far away from the OMe. So, this will be the major product that is formed in this nucleophilic substitution reaction. Sorry, nucleophilic addition reaction. Nucleophilic substitution reaction. NH2 is substituting Cl minus. So, the correct answer will be option B. Is this clear?
Yes, ma'am.
Okay. Now, coming to question number 10, which among following compound will not react under the standard Friedel-Crafts alkylation reaction condition? So they have given four different alkyl chlorides. So which among the following compounds will not react under the standard Friedel-Crafts alkylation reaction condition? So, before going into finding the answer, we should know the limitations of Friedel-Crafts alkylation reaction. So, coming towards the limitations of Friedel-Crafts alkylation reaction, here, since the carbocations that are formed by aryl or vinyl halides, carbocations that are formed by aryl or vinyl halides, they are extremely unstable. So, they cannot be used in this reaction. Then the presence of a deactivating group on the aromatic ring, such as NH2 group, can lead to deactivation of the catalyst due to formation of complexes. If NH2 group is present in the aromatic ring, it can coordinate with FeCl3, leading to formation of complexes that we have seen in last week when we were discussing assignment problems. Then an excess of the aromatic compound must be used in these reactions in order to avoid polyalkylation. So in case of Friedel-Crafts alkylation reaction, we have to use more of the aromatic compounds. Otherwise, alkyl groups can add on more than one position of the aromatic compound. Then aromatic compounds that are less reactive than monohalobenzenes do not participate in the Friedel-Crafts alkylation reaction. If aromatic compounds are less reactive than monohalobenzenes, they will not participate in Friedel-Crafts alkylation reaction. So these are the limitations of the Friedel-Crafts alkylation reaction. Now coming back to our question, which among the following compound will not react under the standard Friedel-Crafts alkylation reaction conditions? So I think you might have got some hint from the limitations we have discussed. So what will be the correct answer? Yes, option 1 is the correct answer. This is a vinyl halide. So it will be forming carbanion, sorry, carbocation that will be extremely unstable. So it cannot undergo Friedel-Crafts alkylation reaction. So option 1, because this is a vinyl chloride. aryl or vinyl halides, they will not undergo Friedel-Crafts alkylation reaction. So the correct option is option A. That is 1. Is this clear?
Yes, ma'am.
Okay. Now coming to question number 11. Which one of the following undergoes nucleophilic aromatic substitution at the fastest rate? Option 1 is the correct answer. Option 1 is the correct answer because nitro group will be highly electron withdrawing in nature. So uh, it can undergo this addition elimination reaction at a faster rate because this NO2 can involve in conjugation, and hence this elimination of chlorine will be more easier in case of option 1. So the correct answer is option 1. Any doubts?
No, ma'am.
Okay. Now coming towards question number 12. Which position will be attacked most rapidly by the nitronium ion when the compound undergo nitration with HNO3 H2SO4? Option D. Option D is the correct answer. Here this OCH3, this lone pair of electrons, it will push in this fashion. It can go and attack on the N double bond O, double bond O plus. Here the para positions are not free. So option D will be the correct answer. Any doubts? Similar
No,
questions.
ma'am.
Similar
No, ma'am.
questions we have discussed previously. So I think this will be easy for you to solve. Now coming towards question number 13. Some meta-directing substituents in aromatic substitution are given. Which one is most deactivating? So we have seen that some meta-directing substituents in aromatic substitution reactions, they are most deactivating in nature. So here out of this four, the correct option will be nitro because of the electron withdrawing nature of the nitro group. Nitro group is highly electron withdrawing in nature. Because of that, this meta directing substituents will be most deactivating in case of electrophilic aromatic substitution reaction. Is this clear? This nitro group will be highly electron withdrawing in nature compared to all the other three given. So because of that, it will be undergoing, or it will be the most deactivating directing substituent in case of aromatic substitution reaction. Any doubts?
No, ma'am.
Okay. Now coming to question number 14. So which of the following drastic condition is required for substitution in haloarenes? We have found the nucleophilic aromatic substitution of haloarenes. So they were requiring harsh conditions. So which of these conditions are required for the substitution in haloarene? High temperature, high pressure, strong concentrated reagent, all of the mentioned.
Option D.
Option
All of them mentioned.
okay, all of the mentioned is the correct answer. So for substitution of haloarenes, we require drastic conditions like high temperature, high pressure, presence of strong concentrated reagents like sodamide in liquid ammonia, etc. So all these conditions are applicable for the drastic conditions that are required for substitution in haloarenes. Now coming to question number 15. Arrange the reactivity of the given compounds in decreasing order for addition followed by elimination reaction. So parachlorobenzaldehyde is given, parabromobenzaldehyde is given, parafluorobenzaldehyde is given, para-iodobenzaldehyde is given. So this sort of problem was discussed during the lectures of addition elimination reaction. So you will be able to find the correct answer from the codes that are given below. So first will be 1, 3, 2, 4. That is the decreasing order they are mentioning. Then 1, 3, 4, 3, 4, 2, 3, 1, 4, 2, 3, 1, 2, 4. 1. So 1 means chloro will be the most. Next will be fluoro, then bromo, and sorry. Next will be fluoro, then bromo, and then iodo. So we will see what is the factors that are directing here. So here we can see the fastest reaction in case of this addition elimination will be taking in case of fluoro compounds. Then comes chloro, which is approximately equal to that of bromo, and these chloro and bromo will be greater than that of the iodo, which is lowest reaction. So when we are considering addition elimination reaction, we will be thinking fluorine is like highly electron negative in nature, so it will be least living group. Comparing the living group ability of the halogens, fluorine will be the least living it will be having the least living group ability, right? We will be considering like that. But the reaction, addition elimination reaction, is taking place fastest when there is fluorine as the living group compared to that of chlorine, bromine, and iodine. What is the reason? So, this is taking place in two steps, right? First, addition will be taking place, leading to formation of an intermediate, and then elimination will be taking place. So, here the rate determining step is this addition step. Rate determining step is addition step. So in case of elimination step, fluorine can slow down the reaction compared to that of chlorine. But it accelerates the first step simply by its enormous inductive effect. Because fluorine is highly electron withdrawing in nature. So by this enormous inductive effect, um, it stabilizes the anionic intermediate that is forming by acceptance of the electrons from the benzene ring. So if we are considering addition elimination reaction, so we can consider the example that we are having C double bond O H. So a nucleophile is coming, a nucleophile is adding. So here the phenolate will be forming. Nucleophile, fluorine, here double bond O minus H. So here this is the intermediate that is forming. So this negative charge will be stabilized by the enormous inductive effect. This is fluorine is highly electron withdrawing in nature, so it will withdraw electrons by means of inductive effect. So this fluorine will be stabilizing this intermediate. So because of that, the like intermediate energy will be coming down. So rate of the first step will be faster when fluorine is present. The fluoro compound reacts about 10 power 2 to 10 power 3 times faster than the chloro or bromo compounds, and the iodo compound is even slower. So since the first step is the rate determining step, so and the fluorine is stabilizing the intermediate, so the fluorine will be enhancing the rate of the reaction in case of this. Okay. If we consider the four intermediates that are present, the intermediate where the fluorine is present will be lower in energy. So don't want to climb the hill more. That is why rate of this reaction will be faster. So in case of reactivity, first will come fluorine, then comes chlorine, then comes bromine. Chlorine and bromine are approximately equal, and the least will be that of the iodine. Here, leaving group ability. Leaving group ability of the halogens doesn't matter because the rate determining step, that is the RDS, is the addition reaction. So the fluorine, because of its highly electron withdrawing nature, it will stabilize the negative charge that will be present in the intermediate by inductive effect. So the rate of the reaction will be greater in case of fluoro, then comes chloro, then bromo, and then iodo. So the correct option will be 3, 1, 3, 1, 2, and 4. Option 4 will be the correct answer. Anyone having any doubts?
No, ma'am.
Is it clear?
Yes, clear.
Okay. Now coming to question number 16, which is based on IR spectroscopy. What is the correct increasing order of stretching frequencies for C triple bond C, C double bond C, and C single bond C, which is having higher stretching frequency? So out of C triple bond C, C double bond C, and C single bond C, which will be having greater frequency, greater stretching frequency, which will be having. So we can consider the equation nu proportional to root of F by mu, where F will be denoting the force constant. So if the so in case of alkyne, force constant will be more compared to that of alkene, compared to that of alkane. So which will be having greater stretching frequency? Alkyne, alkene, or alkane?
Alkyne.
Alkane will be having greater stretching frequency. Then comes
Double bond.
double bond. And then comes the single bond. So the correct answer will be option B, stretching frequency. So here we should use the uh, like equation that nu proportional to root of f by nu. Here the k is used instead of f. So nu proportional to root k, where k is the force constant. So force constant trend is like triple bond greater than double bond greater than single bond. So in case of triple bond, the frequency will be greater compared to double bond compared to single bond. So the correct option will be option B. This is clear. Any doubts?
No, ma'am. No.
Okay. Now coming towards the last question. So, in the IR spectrum, the carbonyl absorption band for the following compound appears at. So, this is a question from CSIR Net December 2011. So, what will be the carbonyl absorption frequency of this compound? So, here a cyclic ester is given and four different frequencies are given. Option B. Option B will be the correct answer. Why? So let us see the let us see the values for carbonyl absorption. So in case of amides, the CO stretching frequency will be coming around 1680 centimeter inverse. In case of ketones, it will be coming around 1715 centimeter inverse. In case of aldehydes, it will be coming around 1725 centimeter inverse. In case of carboxylic esters, it will be coming around 1735 centimeter inverse. For carboxylic acid, it will be coming around 1710 centimeter inverse. For acyl halides or C double bond O X, it will be coming around 1800 centimeter inverse. For carboxylic anhydrides, it will be coming around 1820 and 1760. So here they have mentioned the quoted frequencies are for typical open chain saturated hydrocarbon chains. Conjugation and cyclic structures will influence the absorption frequency. So here they have mentioned the absorption frequencies for open chain open chain carboxylic compounds. But if conjugation or cyclic structures are coming, the absorption frequency can change. So in our case, in our question, we are having a cyclic ester. So normal ester will be having a stretching frequency of around 1735 centimeter inverse. But in our question, we are given a cyclic ester, that is a 5-membered lactone. So for the lactones, the esters that are non-cyclic esters, it is given 1740 plus or minus 10 centimeter inverse, as we can see here. For this compound, the stretching frequency for C double bond O is 1749 centimeter inverse. For a 6-membered lactone, it is coming around 1740 plus or minus 10 centimeter inverse. Here we can see 1740 centimeter inverse for the 6-membered lactone. For a 5-membered lactone, it is coming around 1765 plus or minus 10 centimeter inverse. So here the 5-membered lactone is having a value around 1775 centimeter inverse. And if a 4-membered lactone is present, it will be having a value around 1840 plus or minus 5 centimeter inverse. So here the 4-membered lactone is having a value around 1818 centimeter inverse. So in our question, they have given a 5-membered lactone. So as we have seen in the table values, we can conclude that the value of the IR spectrum for the carbonyl absorption will be coming around 1770 centimeter inverse. So is this clear? So we should have an approximate idea around which the carbonyl peaks will be coming for each compounds. So if we are having that idea, we will be able to solve this question. So this is all what we are having to discuss in this lecture. If you are having any doubts, you can ask now, or else we can meet next week, Saturday at the same time. Any doubts? No doubts? Thank you all for spending your time
Thank
for
you, ma'am.
this lecture. Thank you
Thank
so
you,
much.
ma'am.
Thank you, ma'am.
Thank you.
Ma'am, these all questions are written in assignment.
These questions are from previous year assignments, but some of the questions are repeated in this assignment as well, I think. So I think this will be helping you to solve the assignment.
Can we write the assignments on this question?
What?